Hello, everybody. My name is Scott Wilson. I'm here from a company called SIF Science, and I'm going to talk to you today about our continuing journey of scaling our HBase installation with almost zero downtime. So, what is SIF Science? So, the goal of SIF Science is to be the trust platform of the internet. And what we actually do is we help our customers who are online businesses separate good users from bad users. And so you can see some of our customers here on the right. We do this with a whole lot of data and a whole lot of machine learning, which is really fun. So we were founded in 2011. We currently have a total of 160 employees, but we are always growing. So how does this actually work? So SIFT is essentially a whole bunch of APIs that we provide our customers. So one of the ways our customers send us data is from their application backends. These are events like, hey, somebody added something to their cart, somebody placed an order. Another way we get data from our customers is they can integrate our JavaScript snippet into their web page. And so this way we actually get the browsing activity of their users, which is actually a very useful predictor for fraudulent activity. We also get this for their mobile applications if they integrate our mobile SDK. And so all of this data feeds into our backend infrastructure, and it's all stored. And then whenever a customer is interested in knowing the score of a given user, say they just placed an order or whatever, they send a request to us. We grab a whole lot of data about the user from our infrastructure, send that into our machine learned models, and then we pop out a score for that user. And so you can see Bob here has a score of 27, which means he's probably not fraudulent. So behind the scenes, this is a whole lot of HBase. So HBase is really our primary data store where we keep almost all of our data. And so one of the interesting things about the way we use HBase is that an individual scoring request, say we're trying to score an individual user, we can actually have that individual request fan out to dozens of requests to HBase. And so we have a pretty high query capacity on our HBase cluster. So we actually have 4 clusters total, 2 tiers with 2 replicated pairs, and a total of 1.9 petabytes of capacity on HDFS. We have, at peak, we're doing around 600,000 requests per second. We're currently running CDH 513, and we're on AWS as well. So one of the interesting things about our use case is we have very strict latency and availability requirements. So on the latency side, one of the ways our customers actually integrate with us is when actually somebody clicks checkout and wants to buy an item or whatever, they need to know in that moment whether they should block that transaction or not. And so that has to be a very quick call to our server and actually return very quickly. So all of those HBase requests have to happen very quickly in order to produce that score. We also have very strong availability requirements, and it really boils down to one thing. When we're down, our customers lose money. This is a very dollars and cents sort of thing. Basically, if we're unable to produce a score for a user, they either have to allow all transactions or block all transactions. Neither one is great from a business perspective for our customers. So last year, my colleague Micah was here, and he gave a talk called Highly Scalable HBase, kind of along similar lines as what we're going to cover today. But kind of today we'll be talking kind of the next evolution of what we've done. So in order to kind of set the context for today's talk, I'm going to quickly review a couple of the things that we covered in last year's talk. If you want to know more about these, the slides are available there, and there's also a YouTube video, which you can go back and look at. So one of the things we actually did to improve our reliability is added circuit breaking into our HBase client library. We did this with Hystrix. Basically, this is a way of preventing a problem where all of our application threads would get tied up talking to a single region server that was having problems. And it kind of prevented our applications from moving forward even if there was a single region server experiencing issues. So the way it does this is it actually monitors all the requests to each individual region server and sees if there's a whole lot of failures going to one, it'll actually break that circuit and will fail fast any additional requests to that region server. And then obviously it's able to detect, or it allows a few requests to go through, and if they're successful, then it recloses the circuit and allows those requests to go through. So this was a big win. But really the biggest thing we did was to create a second replicated cluster. And so we have this production cluster, and we added a second one. And we set up bidirectional replication. This is probably a common pattern that a lot of you have seen before. And the way we make this work is we have all requests go to a certain primary cluster that we designate. This allows us to keep the consistency requirements that HBase provides around read and write consistency, which is very useful for us. But the application actually maintains connections to both clusters at all times, so it can quickly fail over. And so there's also a process that we have of online verification. So we mirror a small percentage of the requests to the secondary cluster, and then we actually make sure that those requests are successful and actually match what we see in the primary cluster. That allows us to get a lot more confidence that that secondary cluster is actually still in sync with the primary. So generally the setup has a lot of advantages: availability, being able to do easy cluster maintenance, and it's just significantly better. So how does this actual process work when we want to change the cluster? So let's say cluster 1 experienced problems. The state for who is the primary cluster is actually kept in Zookeeper. So we update the Zookeeper node. The applications actually all have watches on that specific Zookeeper node. And so that way they're very quickly notified of that change and begin sending all of their requests to cluster 2, which is now considered the primary. So how did this help? Obviously, it helped a lot. We had a lot of downtime before. These were some major HBase problems. And the problem is, like, when you have one cluster, if you have a problem that takes many hours to recover from, that's all downtime. But once you have a second cluster, you can very quickly fail over to the secondary and then have that primary, or the old primary, down for maintenance, basically. So this was a bit of a before and after in terms of our uptime, which really significantly helped a lot. So the first thing I'd like to talk about today is how we've improved the process of this cluster failover. We had a bit of a process before, but we've made some significant improvements to how that's actually done. So digging a little bit more into how failover is actually executed. So generally what happens is the cluster experiences problems, an on-call is paged for some kind of problem. They have to look at all the dashboards, figure out the source of the problem, see it's an HBase problem, figure out which cluster it is. They have to pull up the playbook for doing the failover. They have to make sure the standby cluster is actually healthy by looking at a whole lot of graphs. Then they have to actually run the failover command on their local laptop by checking out the code and assembling a command. Then they have to post in the Slack channel saying, hey, like, I'm going to do a failover. And then they actually have to run the command. So it's a bit of a complicated process, and so there's also this fear element. So this is an important part to kind of when you're on call, especially when you're kind of a new on-call person. You really are a little bit afraid that you're going to make things worse, especially if we're not in like a full down situation. So this is definitely an issue we saw creeping up a lot, where people are like, should I do the failover? Does it look safe? And there was a lot of like confusion and fear around it. So both of these things have actually added together to really create kind of pretty long recovery time compared to what we would like to see. So the goal here is to really reduce our mean time to recovery. So what do? We tried to fix the complicated process part by making it a lot simpler to actually execute that failover. So we just added a web UI. So all of these steps on the left turned into just open up our Eng portal and actually click a button and the failover will happen. And that's all you need to do. But we also wanted to address this fear side of the equation as well. So we wanted to make sure that the on-call person knows that it's safe to fail over and has a lot of confidence in that and isn't hesitating when they want to push that button. So we make it very clear in the UI whether it's healthy or not. And so we actually try and prevent that failover if it's unsafe. And so what are the actual checks that we go through to ensure that secondary cluster is safe? The first one is to actually make sure that we have replication enabled in both directions. Because if you don't have replication, then you can start losing edits, and that cluster needs to be rebuilt, which is no fun. You want to look at the age of last applied operations. This is one of the statistics that HBase region servers themselves produce to say this is how old the last operation I just applied was. So that's on the target side. On the source side, we also want to look at the replication log backup. So this is the number of walls waiting to be replicated before it actually catches up to the current. So we want this to be 0, obviously. We also look at the online verification stuff that I was talking about earlier, where we actually compare the result from the secondary cluster to what we get from the primary cluster and make sure that those are both successful and they actually match what's in the primary cluster. We also want to make sure there's no regions in transition. This is a kind of common HBase failure case where regions are currently unassigned because something went wrong in the reassignment process. And so obviously that would manifest itself in client errors if we actually did fail over to that cluster. So this helps, both of these steps have definitely helped a lot in terms of making this manual process a whole lot easier and a whole lot safer. But what if we could do it automatically? So our goal is to actually take it one step further and actually fully automate this process. Because at the end of the day, the human operator is just looking at metrics to try and decide whether to do this, and we can automate a lot of that. So what we did is we created a new service that we call Overwatch, and what it's responsible for is just watching the health of both clusters. So I'll go through the example here of, let's say HBase 1 is currently active, and it starts experiencing problems. A few region servers died, let's say. And so Overwatch notices that. It also notices that HBase 2 is currently healthy, so it wants to trigger a failover. So then it goes out and triggers the failover, updates Zookeeper, and Zookeeper informs the application, and now the application is now sending all requests to HBase 2. So once again, we have a certain set of checks that we want to ensure that the primary cluster is passing. Or if any of these checks fail, then we actually want to trigger that failover. So first thing is obviously client error count. So if you're seeing actual errors or timeouts from the client side, then you probably want to fail away from that cluster. But we also want to look at just client latency. So we actually look at 99p client latency. Because there's a lot of cases where you may have slow performance on a cluster that doesn't necessarily manifest itself as errors or timeouts, but you still want to actually fail away from that cluster because you're not getting the performance that you want out of your cluster. So another very important check is to actually look at the history of failovers and ensure that there hasn't been a recent failover. So the goal of this is to actually prevent the case of flip-flopping back and forth, where you're just failing back and forth between the clusters. So we actually store this history in Zookeeper. We just keep the last 10 or so failover in Zookeeper. And this we put it in Zookeeper because we already are using it as a data store in this system. So we didn't want to add a secondary data store just to save history. So it actually works out pretty well, and it's a lot smaller surface area. So then on the safe to fail over side, we actually reuse that exact same check from the previous step of this cluster is safe to fail over to. And so obviously this works very well for the kind of simple case where you have one cluster experiencing problems, another cluster being healthy, ready to fail over to. But there's a lot of other cases where things can go wrong. And so those are the much larger surface area. That's when we really need to get a human in the loop and actually want to rely on their judgment for how to proceed next. And so we actually go ahead and page the on-call and get them involved. So where are we at with this? Currently, we are implementing step 3. We've implemented steps 1 and 2. But once we get step 3 fully implemented, we really believe that this will significantly improve our mean time to recovery. So I don't have numbers to share with you about how this has helped yet, but maybe next year. So the next major topic I want to talk about was kind of a trade-off that you have when building your HBase clusters of kind of cost versus performance. So this is a kind of fundamental thing that you have to deal with when you're creating your clusters. So kind of give a little history here. Sift started on hard disk backed clusters. We were on D2 instances, for those familiar with AWS instances. We liked it from a cost perspective, but the performance wasn't amazing. And so we have a whole lot of random reads, and we thought that switching to an SSD cluster would actually significantly improve our random read performance. And so that's exactly what we did. We switched to an SSD cluster. And as you can see, we definitely saw very significant performance improvements, kind of a 3x drop in 99p latency and 5x drop in 95p latency. But as you might guess, we just started throwing money at Amazon to solve the problem. So we started thinking a little bit more. And we kind of have this classical trade-off. On one side, you have this sort of fast, expensive option, and that's the SSDs. The i3 instances are about 4x the cost per gigabyte as opposed to the D2 instances. So obviously a very expensive option, but we still really would like that performance. And on the other side, you have this kind of slow, cheap option, which is hard disk drives. So we started thinking of ways to try and get the best of both worlds here. And so we looked at our data, and we realized we really have kind of two major tiers of data. There's one set of our tables which have very, very strict latency requirements, and we called these the fast tables. And these were the tables that were generally involved with the online scoring paths. So whenever we wanted to produce a score for a user, that's the operation we want to be very fast in the system. And so those are the tables that we wanted to call fast. And this worked out to be about 35% of our data. So there was a lot of possibility for kind of some wins here. So we also had this other tier with looser latency requirements. We called these the slow tables. And so we actually, these are the kind of tables that will actually be powering some of the web console tools that we give our customers to be able to look at our data at a much more detailed scale than just getting a score for a user. So what we went about is try to create multiple tiers of data. So we called this project the multi-tier storage project. So what we started with is just one combined tier, and that was backed by SSDs. We have 2 replicated clusters, which I kind of explained earlier. And the first step here was to actually logically split our tables between fast and slow. And so what this meant is, inside of our application code, we actually started designating tables as either fast or slow. And then we changed our configuration to be able to support different clusters for fast tables versus slow tables. And so we started with the combined tier on SSDs. And then the next step is to spin up the first cluster in the slow tier. And so we put just the slow tables on this new slow cluster. And we set up replication for those slow tables from the fast tier. Now in this stage, all requests are still going to this fast tier, but it allowed us to gracefully spin up this slow tier cluster and get it to a state where it was ready to take requests. So then we started sending it requests. And the great thing about this sort of replication path that we have here is we can always fail back to step 2. Let's say this cluster experienced a little bit of a performance hiccup, which it did several times. We could always fail back to this one, which was a great property to have. So once we got that up, then we spun up the second cluster for the slow tier and set up replication there. And this allowed us to have our high availability pair of clusters in the slow tier and allowed us to move on to the next step of fully separating these tiers. And so basically we got rid of the replication between the tiers and we removed the slow tables from the fast tier. And this is the step where we could actually scale down these SSD clusters to a much smaller size. And this is where we got the cost wins. And does anybody want to guess how much we saved on this project? 52% reduction in HBase cost. So this was a very significant win for the company's finances. Obviously, our business operations team was very, very happy with this. And it kind of got our gross margins back in the order that we wanted them to be. But this wouldn't be an HBase talk if there weren't bumps along the way. So one issue we ran into was around remove peer. So remove peer is the thing that says, I no longer, it's an HBase shell command that you run if you no longer want to replicate to an external peer or an external cluster. It should be a safe command. We've run it many times, but for some reason, one time when we ran it, it actually caused half of our region servers in a cluster to crash. And so the root cause, kind of digging around, appeared to be Zookeeper watches actually not getting fired in those region servers to say this is no longer a peer to replicate to, and actually essentially had a null pointer exception and bubbled up and crashed the region server. So we also had an issue with disable table replication, which is the thing that says I no longer want to replicate this specific table. One time we ran this, it caused a weird situation where a bunch of regions got stuck in transition, and we tried to fail over to another master, and that master actually got deadlocked in its startup logic. And so the only way we saw to actually clear this problem was to fully shut down the cluster and actually manually remove these Z nodes in the regions in transition directory. That was the only way we found to actually recover the cluster and allow the master to start up and get the cluster back to health. Another kind of odd thing we noticed was four-way circular replication. Originally in this step, we had a replication between these two write clusters going vertically. That seemed to cause performance problems. We didn't see this problem when we had three-way circular replication, but for some reason with four-way circular replication, there was something about it that caused more performance problems. So we just severed that link, and we didn't really need it anyway. So that was kind of an easy fix for that one. Cool. So multi-tier storage went very, very well. The next major topic I'd like to talk about is a couple of the tools that we've actually been writing to kind of improve the way we deal with our HBase clusters and get more visibility. So late last year, we kind of saw this, we started having this very odd problem where we saw very wild swings in our HDFS usage. And you can see it's on the order of like 20% or something here, which is pretty crazy. This is just on the order of about a week. And so we were very puzzled by this for quite a while. We investigated it as an HDFS issue. That kind of led nowhere. Eventually, we looked a little bit closer at HBase and added a lot finer grain monitoring for the different data directories inside of HBase, the HBase directory on HDFS. And once we saw the archive directory usage over time graph, it was very obvious that that was the source of the fluctuation. So for those of you that aren't aware of what the archive directory is kind of the, not quite the trash directory, but the staging directory before HBase actually deletes the files. So once an H file is no longer needed on the read path, like let's say there was compaction run, and you no longer need that H file, it's moved into the archive directory. And then it's later deleted. So how do these archive files actually get deleted? So we dug into the HBase master code and found cleanerchore. So this is the thing that runs inside of HBase master, and it is responsible for doing all of the cleaning of the archive directory as well as the old walls directory. So importantly, it is actually only single-threaded for each one of these types. So there's actually only a single thread that is responsible for deleting all of your old H files that are produced by your cluster. And so what happened for us is we have quite a few regions, and that means a lot of H files, and so that single thread was no longer able to keep up with the rate that we were actually producing these H files into the archive directory. So the good news is this has been fixed in HBase 2.0, but we are not running HBase 2.0. So we had to write our own tool to actually make this cleaning multi-threaded. So we created what we call the archive cleaner. We run it via cron every 30 minutes or so. And basically what it does is it scans through the entire archive directory. It does this multi-threaded, so one thread per table will scan all of the files under that table's archive directory. And then it puts all of those files onto a queue. And then there's another thread pool where we run around 80 threads or so. And those threads are responsible for reading each and every individual file, deciding whether it's actually safe to delete. And so it does this by actually reusing the same logic that cleanerchore does. It uses specifically the HFile link cleaner and time to live HFile cleaner classes. So we had a lot of confidence that it was using the exact same logic that cleanerchore was using, so we thought it would be pretty safe. But as an extra safety mechanism, instead of immediately deleting the files, we were actually moving these into our own trash directory. And so we actually had a separate job that ran later that actually cleared the trash. And this kind of allowed us to roll it out with a lot of confidence. So let's say we messed up the logic on actually deciding whether something is safe to delete. Then the cluster might say, oh, I'm missing this file and have problems. But if we saw that, then we could very easily restore those files from this trash directory. And that gave us a lot of confidence when we were rolling this out that we could do it safely. One interesting wrinkle here is there's a whole other set of logic for determining whether the H file, if there's a snapshot associated with a table, whether the files in the archive directory are safe to delete. That was a little bit more complicated than we actually wanted to integrate into this tool. So we actually kind of just ignore any tables with a snapshot associated with them. That works well for our use case because we generally don't have snapshots sitting around on our clusters. We actually export the ones we want to save to S3, so they're never just sitting around on our cluster. So this has been a great thing. We're hopefully planning on open sourcing this soon, so if anybody else has problems like this, hopefully they could use the same tool. So another thing we try to tackle is try to get finer grained request metrics. So HBase provides at a region level what are all the read and write request volumes. But we wanted to go a little bit finer grain than that. So basically we instrumented our HBase client to actually track on a very small key range basis what are all the requests going to that key range. And so it buffers this in memory, and then we'll actually flush it to an HBase table. And so then we get a historical view of, on a per key basis almost, what the request volume is. And so from this, we can generate a heat map like you see here. This is actually a heat map of what you want it to look like. It's generally well distributed across the whole key range here. But having heat maps like this make it a lot easier to help debug hot region issue or hot key issues. And so the next step that we want to take this is we actually want to integrate this into our region splitting tool. So basically, normally when you split a region, you kind of have to just split it right in the middle, and that may not be where the hot range is. But if you can use this data to figure out exactly where that hot range is, you can split it right in the middle there and hopefully separate out that hot region onto multiple region servers. So wrapping up, a couple takeaways here. Two major topics were reliability and cost. So for reliability, replicated clusters have been an amazingly great for us. I cannot express to you how much easier it is to operate a system where you always have a spare to fail over to if you have problems. But then the next step after that is to really look at that failover process. And if possible, you want to automate that. And that's where you really get the gains of having both of those clusters and always having that spare to very quickly fail over to. So the other side is the cost side. So SSDs are great, but they are very, very expensive. So just be aware of that. But if you have a similar use case to us where you have this kind of multiple tiers of data with different latency requirements, then doing this sort of hybrid environment with multiple tiers can actually save a very significant amount of money. So I would be remiss to say if I didn't mention that we are hiring. We are always looking for people to deal with HBase scaling issues. So come talk to me after or visit this website. And that's it. Thank you very much. And any questions? You can go to the mic. There's a switch there on it, I think, on the top.
Now? Okay. Did you use HBase replication or did you use a third-party replication
Yes, this
tool?
is built-in HBase replication. I should have mentioned that.
And
Sorry.
no latency or performance issues with, the writes being available in a timely manner in order to support your failover?
Yeah. So that's a very interesting thing when thinking about a system like this, is you want these sort of consistency requirements of always going to a single cluster. So that's why we direct all requests to a single cluster. And then basically, there is this time when you're actually executing the failover that you may have a little bit of consistency issues, but for our use case, we were kind of okay with dealing with that very small window of consistency issues when failing over, since it's a relatively rare event. But in terms of performance of replication, it's generally pretty good. It normally sits around 100 milliseconds or so, or less. Exactly. So we put it as part of this check of age of last applied operation. So that's the check there, is to make sure that. Yeah, we're entirely on one AWS region. So we don't have the problem of cross-region replication yet. We have not tried cross-region replication. It's something we plan to do in the future, but we have not done it yet.
Hi, can you elaborate on the more granular client key range metrics?
Yeah, so basically we kind of decided what, like for across the entire key range, what are the smallest like granules that we would be willing to like produce metrics for. And so I think it's like a byte of the key range or so. And so we keep track of all the requests for that byte of key range. In the client, yeah. And then that's flushed to the HBase table, like a separate HBase table.
So currently I have exactly the same kind of a setup that you have, and our application is cross regions. We have, everything is on-premise, nothing is in cloud. So we have replication from west to east, and that goes fine, except we are on the older version of HBase, which has issues with data loss, but that's the HBase that is resolved in the next releases. But my question for you is, I'm very interested in this automated failover that you have. Currently, we are doing a manual failover, and it's a pain in the neck.
Yeah.
So is that like a custom code that you guys
Yeah,
came up with?
yeah, so
because you showed high-level metrics, and I have those, but I don't know how do I use them to make it automated process.
Yeah. So I mean, the first thing is doing that safe to fail over check, and I kind of went over all the different things that we're looking at. This is what we've implemented so far. We're still in the process of implementing this automation step. And so basically, it's a kind of union of these two, of saying like this cluster, the current primary cluster is deemed to be unhealthy, but we are safe to fail over to the other cluster. And so we actually have this Overwatch service, which is actually a Java service, that will be ingesting those metrics, looking for anomalies, deciding whether it's safe or not, and then actually triggering that event.
So the interesting part is that Overwatch writing to Zookeeper.
Yeah, exactly.
Something I guess I don't understand.
Yeah. So basically, on the back end, this is actually just a bunch of Java code that will be. The Java code will actually update Zookeeper, and so it's just saying like updating this config, saying the current cluster is now this. So it's just writing a Z node with that data, and that's really all it's doing at the end of the day.
Just creating a new Z node.
It's not a new one. It's just actually updating the current one to say like there's a Z node that says this is the current master.
Thank you.
Regarding the archive file, so you just run the cron and just delete the archive file. That's what I heard. Just plain cron, like.
Yeah. This is just a cron job that we run. So we created like this is all basically the. Come on. Yeah. So basically, it's just run every 30 minutes. It's a process that starts up. It scans through all the files in the archive directory, sees which ones are safe to delete, and then actually deletes them.
How do you check the safety?
Yeah, so we reuse the logic that's used inside CleanerChore. So inside CleanerChore, it's actually got a number of different classes that it looks at, and it makes sure that all of them consider it safe to delete. And so it's just a union of all of those saying, like, this is safe to delete. And we reuse those exact same checks the exact same code. So we like have linked, like we have the HBase server jar in like linked inside of our Uber jar.
So between your two HBase, how do you make copies? Which tool?
Are you talking about creating a new one?
No, the duplication.
So the duplication, that's just the replication between the clusters. So it's just the built-in HBase replication. So we have peers set up in both directions. So any edits going to either one will be propagated to the other. If you're wondering about the process of bootstrapping one of these, that's a separate thing. Basically, we normally just go from S3 backup. So we restore that S3 backup onto the cluster. Then you take a snapshot and you enable replication, and then you export that snapshot over. So, all right, thanks very much.